In the previous lecture we had started talking about the beam problem. So, and what was the difference between the beam problem and the bar problem that we had done earlier? The difference is that the beam problem is a fourth order differential equation. For this we had defined the weak form. We had also talked about the boundary conditions that are possible, and we had started talking about the shape functions that need to be constructed at the element level, the minimum order shape functions, in order to satisfy the C1 continuity that is imposed by the smoothness requirement that comes out of our weak formulation. So we had said that we are going to construct the so-called Hermite cubic polynomials, which we had said at the element level will lead to an interpolation of the value of, so if this is my x1 of k element and this is my x2 of k for the element ik, so it would lead to an interpolation of the value of the displacement at the element level and dv1 dx at the element level. Okay. Similarly, at the two nodes v2 and the derivative here. So, value and the derivative or the slope and the value and the slope at the two ends of the element. So, we need to interpolate between the four values, and the minimum order polynomial that will interpolate four values will be a cubic. That is why the starting set of polynomials, the minimum set, is a cubic polynomial, as compared to what we had in the case of the bar problem, where the minimum order polynomial was the linear, piecewise linear. So, remember that here we start with a piecewise cubic. So, we had said that essentially we will write v of x is equal to v1 over the element ik, v1k into n1 k plus this dv1 I am going to call it as theta 1 of k, theta 1 k n2 k x plus v, the displacement at the other end, transverse displacement, v2 of k n3 kx plus this I am going to call as theta 2k, theta 2k n4k, the function of x. So, now it is a question of constructing these polynomials. So, if I go ahead and take Vx, as I had told you earlier, is equal to some alpha plus beta into x minus x1 of k plus gamma into x minus x1 of k whole squared plus delta into x minus x1 of k whole cubed. If I took this expansion, which is a cubic, here I go and satisfy those conditions, I should be able to obtain the constants alpha, beta, gamma and delta, and from these constants I should be able to rearrange everything in terms of the v1k, theta 1k, v2k and theta 2k, and I will get out of that n1k of x is equal to 1 minus 3 into x minus x1k by h k whole squared plus 2 into x minus x1k by hk whole cubed. Similarly, n2k as a function of x comes out to be minus x minus x1k over hk into 1 minus x minus x1k over hk whole squared, this whole squared into hk. So, I can effectively cancel this hk out, take this one out. N3k of x becomes 3 into x minus x1k by hk whole squared minus 2 to x minus x1k by hk whole cubed. Similarly, my n4k as a function of x comes out to be, okay, n2k will have this plus sign here, I have a mistake there. Again here it will be x minus x1 of k into minus of x minus x1 of k by hk plus x minus x1 k by hk whole squared. So, my n1 k is 1 minus 3 x minus x1 k by hk whole squared plus 2 x minus x1 k by hk whole cubed. N2 k is x minus x1 k into 1 minus x minus x1 k by hk the whole quantity squared. N3 k is 3 of x minus x1 k by hk whole squared minus 2 x minus x1 k by hk whole cubed, and n4x is x minus x1 k into minus x minus x1 k by hk plus x minus x1 k by hk whole squared. These are the 4 functions that we have at the element level. Look at one thing, that these functions n2 of k and n4 of k correspond to the slope, that is dv dx at the 2 points. That is why if you see that, sorry, where is my n2k? N2 of k and N4 of k. In these, there is a difference in the dimension by a factor of hk. That is, this into hk will give you the same dimensional consistency as the N1 or N3. Which, let us now go and look at how these functions look. So, if I am talking of these functions at the element level, the first function n1 of k should be 1 at this point, at the point x1 of k. It should have a 0 derivative at this point, and it should have a value 0 and a derivative 0 here. Why? Because when I put it back in the expression for the value, v at that point becomes equal to v1 of k, the derivative becomes theta 1 of k, and so on. So, because these are linearly independent functions, it so happens that when we take the derivative, we should only be left with the part coming out of the theta 1 of k. So, this function will be 1 here, the value is 1, slope is 0, and it comes down to value 0 and slope 0. This is my n1 of k. Similarly, let us make the similar ones first. N3 of k will have a value 1 here, slope 0. So, N3 of k will be like a mirror image of N1 of k. This becomes N3 of k. Now, let us make the N2 of k. N2 of k, what will it have? If I look at N2 of k, it should have a slope 1 at this point, value 0, and slope and value 0 at this point. Okay, so it should have a slope of 1, value 0, and should come down to this. This is my n2 of k. So if I look at the slope, this angle is 45 degrees, if you want to say that. Similarly, let me make n4 of k. n4 of k will have, it corresponds to theta 2k, right? So it will have a value 0 here, slope of 1 at the point x2, and value 0 and slope 0 at the point x1. So that function is going to look like this. So this is my n4 of k. So these are our 4 shape functions at the element level. Okay, a simple question is, what are then the global basis functions? Because remember, we are still, as far as the approximation is concerned, we are creating these global basis functions which are C1 functions, and the pieces of these global basis functions are these shape functions in the element. So let me draw 2 of these representative functions. So let's take, for example, the function which interpolates the value of the v at this point. So let this be a generic point k. So if I look at this function in this element, so this will be element k, this will be element k minus 1. So here if I look at this, this is going to be my first phi, the global basis function, and then so this corresponds to the value. The second one, let's look at this same point which corresponds to the slope, will have a derivative 1 here. So it is going to do something like this, and this. This is my second function. So corresponding to a generic node k, the first function at the node, the first global basis function corresponding to that node is, I'll call it phi bar, okay, is this kind of a function which vanishes at the ends of the elements k minus 1 and k, and after that it smoothly goes to 0. It stays as 0 everywhere else. The second function, phi double bar, corresponds to the slope being 1 here, okay, which means it interpolates the slope, okay, and you see what it does, it has a slope 1 here, value 0, and it comes down finally at the ends of the elements k minus 1 and k, it becomes 0. So this is how we are going to construct the generic basis functions corresponding to a node k. Okay. So our approximation will be in terms of, so how many basis functions we have now for each node? We have 2, because each node in the case of the C1 approximation has 2 unknowns assigned to it, and these unknowns are the value of the function and the value of the derivative of the function. Okay. So there are, if I have n nodes, then there will be 2n such functions. Okay. So my generic approximation in this case, I can write that V finite element for an n noded mesh is sum I is equal to 1 to 2n alpha I phi I. So corresponding to the node k, which phi I do we have? So corresponding to the node k, it will be actually equal to phi, if you check it out, it will be 2k minus 1, and this will be equal to phi 2k, or we will have the shape function, the basis functions corresponding to the node k are the phi 2k minus 1 and the phi 2k, which goes into the representation of the finite element solution over the whole domain. Now, by the same token, by what we have done here, we have done this. What is then my representation of the finite element solution in the element? Just like we did earlier. So, we will say that VFE in the element K is equal to V1 of K N1 of K plus theta 1 of K N2 of K plus V2 of K N3 of K plus theta 2 of K N4 of K. So, now it is quite easy to see that what is this corresponding to? This corresponds to the global alpha 2k minus 1. This is the piece of the global phi 2k minus 1, because the first node of the element k is the node k. Okay. This corresponds to the global alpha 2k, and this corresponds to the global phi 2k. This is alpha 2k plus 1 phi 2k plus 1 similarly, and this corresponds to alpha 2k plus 2, and this is phi 2k plus 2. Okay. So, we could also write that this is equal to at the element level by renaming V1 k and so on. I is equal to 1 to 4 alpha I of k n I of k, where we understand what are alpha I in the k mean. Okay. So, if I do this convention of renaming the V1 of k as alpha 1 of k, theta 1 of k as alpha 2 of k, V2 of k as alpha 3 of k, and theta 2 k as alpha 4 of k. Okay. What kind of local to global correspondence do we have? So, here if you look at it, so if I write here I 1, 2, 3, 4, this is local, this corresponds to global. Let me write it as big I. Big I is equal to here 2I minus 1, 2I plus 1, 2I plus 2. This is the global. And now it is quite easy to write it in an algorithmic way, that the global I is equal to sorry, the global, actually I have made a mistake here, it should be 2 k minus 1, 2 k plus 1, 2 k. So, this one will be 2 k minus 1 plus I. Okay. If I write it like this, you check that for I equal to 1, this becomes 2 k minus 1, for I equal to 2, it becomes 2 k, for I equal to 3, it becomes 2 k plus 1. So, this I can now load in my IEL DOFs. So, IEL DOFs for the element k, I, for the element k, the local ith degree of freedom is equal to 2 k minus 1 plus I. So, this gives me the local to global enumeration. So, once we have obtained these things, then I have a complete correlation between the element level approximation and the global approximation. Okay. So, if we now see what does the element stiffness matrix and the element load vector turn out to be. Okay. So if you see this, the global stiffness matrix will come from which expression? Okay. This will give me the global stiffness matrix, and this, remember that on the right hand side I have x is equal to 0 to L Fw dx plus the shear force into W evaluated at 0 and L plus the bending moment into W prime evaluated at 0 and L, and this quantity plus this quantity is going to give me the load vector. Remember that as we had done earlier for the second order problem, these boundary conditions we are going to impose later. So this essentially will go into our load vector, this part. Okay. So if I look at first the stiffness part, where is it going to come from? So the stiffness part, this obviously will come from the partitioning over the element k, sum over x1 of k to x2 of k of Ei. I am now writing the second derivatives as double primes, W double prime dx. This is the sum, right? This integral can be written in terms of the sum. Similarly, for the load, I can write sum over the element k integral x1k to x2k of Fw dx. Okay. So at the element level, which are the integrals that are active? It is x1 of k to x2 of k, Ei of x, v double prime W double prime dx, and integral x1 of k to x2 of k q qw dx. Q is my transverse load that I have applied, so I am using F or Q accordingly here. I am mixing the two, but it should be Q because according to the convention for beams, transverse load is generally given the name Q. Okay. So if I look at this, the finite element approximation is replaced here instead of the V. I know the finite element approximation will be equal to the sum of I going from 1 to 4 alpha 2 k minus 1 plus I phi double prime to k minus 1 plus I. Okay. So it is the sum over these 4, and remember that this is equivalent to writing the sum over I going from 1 to 4 alpha I of the element k into Ni of the element k double prime. Okay. Similarly, for the q, I will get it as sum. Well, here there is, in the q there is no sum involved. In the q, I will get the integral as integral x1 of k, x2 of k, q. We will see it is Ni of k x. Okay, because here the W also, what happens? W is also made of these Ni's, because these are the only ones, only part of W which is non-zero in this element. So, okay, so for V I have this representation. For W, now I will write, I will put W equal to N1k, N2k, N3k, N4k, and I will get the 4 equations to which this element is going to contribute. Which columns will it go to? So if I put W equal to N1k, N2k, N3k, N4k, it means which rows it is going to? It is going to the row 2k minus 1, row 2k, 2k plus 1, and 2k plus 2. Columns, Columns will come from this alpha I part. So columns will be the column 2k minus 1, column 2k, column 2k plus 1 and column 2k plus 2. Okay. So now in terms of this element representation, I am going to have the element stiffness matrix kk, which is of size 4 by 4, and the element load vector four by 1. Okay. So let us now give the entries of the element stiffness matrix. It is going to be, we have done enough of this, so we can now go back to what we have done to the previous slide and see that it is going to be EI x n I k double prime n j k double prime dx, and f I k is equal to integral x1 of k to x2 of k q n I k dx. Now the question is that we have done everything at the master element level. So how do I convert everything to the master element level? Again, we are going to put the transformation x is equal to x1k into 1 minus psi by 2 plus x2k into 1 plus psi by 2. If I put this transformation, then in the definitions of n1k, n2k, n3k and n4k, all I have to do is substitute x minus x1 of k is divided by h is equal, h of k is equal to 1 plus psi divided by 2. You check from here that x minus x1 of k will be equal to what? X2 minus x1 of k into psi by 2. Okay, and x2 minus x1 of k is hk. So x minus x1 of k divided by hk is equal to 1 plus psi by 2. I substitute this thing in the expressions of n1k, n2k, n3k and n4k to get my so called n1 hat as a function of psi, n2 hat as a function of psi, n3 hat as a function of psi and n4 hat as a function of psi. So let me write as an example what will n1 of k become. N1 of k will map to n1 hat of psi. This is equal to 1 minus 1 plus psi by 2 whole squared plus 2 1 plus psi by 2 whole cubed. Okay. So with this simple substitution, I am now able to get the definition of these shape functions at the master element level. So if I have the definition of these shape functions at the master element level, then I can convert these integrals to integrals over the master element level. Okay. So how will I convert? So what I will get is kij for element k. Now by doing the conversion, minus 1 to plus 1, ei hats, now it has become a function of psi. Okay. Ni hat double prime nj hat double prime. Now ni hat, because d2n ik dx squared is equal to d2 ni hat d psi squared into d psi by dx whole squared. So, this d psi by dx whole squared is nothing but, as we had defined the Jacobian earlier, 2 by hk whole squared. So, I will have here 2 by hk whole to the power 4, because for each one of them now the Jacobian d psi. So, this is what my Kij is going to look like at the element level. Okay. Similarly, Fi for the element k will look like this: -1 to +1, q becomes now a function of psi. So, I will make it q hat into ni hat into hk by 2 d psi. So, the element load vector entry becomes this. Now, let us see what is the integration rule we have to use. So, we are going to use the Gauss-Legendre quadrature that we had defined. Okay. Now, the question is, what is the order of the integrand, maximum order. So, let us assume, at least for the problems that we are trying to solve, let us say that we have this beam with a rectangular cross section. Okay. Let us say, and for this cross section, this is the height h, this is the width b. Okay. Now, we say that h is varying linearly and b is constant, that is the height varies linearly, that is I have a tapering in the height while the depth remains the same. So, in this case, I as a function of x is equal to 1/12 bhx cubed. So, I varies is a then a cubic, because h is linear. So, I is 1/12 of bh cubed, it becomes a cubic. So, if I is a cubic, if I go back to my integrand here, so ei is a, so if I write it here, ei is a cubic, it is of order 3. The second derivative of ni, since ni was cubic, second derivative is linear, second derivative of nj is linear. So, here the order of the integrand is 5, if I have taken the beam to be a tapered beam. If it is a beam of constant cross section, that is h and b are both constant, then this part will become 0. So, this integrand is essentially of order 2. Okay. Similarly, if I look at Fi, let us say that I am interested at most in a loading which is linear, that is I will have the constant loading and I have the stepped loading, the triangular profile. Okay. So, the loading is linear. So, if the loading is linear, the q is linear, ni is cubic. So, here the integrand is of order 4. Okay. So, let me write here within bracket 2 in case my ei is constant. Okay. So, my integrand p bar, if you remember, will be equal to max of 2 or 4. So, this is equal to either 5 or 4. Okay. With the understanding that it is 5 when I have a tapered beam and it is 4 when I have a beam with a constant cross section. Okay. So, in this case, if the integrand is of this order, then we know that the integration rule, the number of points. So I have to have NINT is greater than equal to P bar plus 1 by 2. So in this case it is equal to, if I take 5 then 3, and if I take 4 it becomes 2.5. So NINT equal to 3 will do our job. So if we take the 3-point integration rule, we will get exact integrals as far as the stiffness part is concerned and as far as the load part is concerned. Okay. So remember that these are procedures which are now very similar to what we have done. So if I want to incorporate this in my finite element program, which I have already written, I do not have to change much. All I say, the preprocessor, you see that the mesh will be the same. Okay. Now the degree of freedom numbering, how will I do? I will go and simply, if it is the bar problem, I will do the degree of freedom numbering according to the bar, where the order of approximation we can choose. In the case of the beam, we are only going to look at the Hermite cubic. We could raise the order of approximation, but let us say it is only Hermite cubic. So we choose for the beam the Hermite cubics, and then we can give the degree of freedom numbering as I have just shown. So the ILDOFs can be created, no problem. After I have done all those things, then I choose the integration points. I have the integration points, and there again at these integration points I can load the values of the shape functions, the derivatives of the shape functions, and now in this case the second derivative of the shape functions also we are going to store. Go to the element calculation, do the element calculation, do the assembly, and continue from there. Okay. So this is how we are going to do the whole procedure. So adding this part to the 1D code should not be difficult. Now what about the boundary conditions? So boundary conditions, so let us take some basic types of boundary conditions. I can have at each of the end the case which corresponds to a clamped end. So here I am saying u is equal to 0 and v is equal to 0 at the point x bar, at the point x bar. Now u, by its representation, it means that through the depth, through the height it is 0, which means that this will give me dv dx is equal to 0, because u0 was 0 for our problem the way we have done it. Okay. So u becomes equal to minus y dv dx. Now for all y this has to be 0, so dv dx is 0. This condition where I am specifying v equal to 0 and dv dx equal to 0 at the point x bar, this is called a clamped end. So we have talked about the clamped end, and this is nothing but our Dirichlet boundary condition, that is both u and v are fixed. We can have a mixture of things also, let us see. So we can also have a second type of boundary condition at this point end, where I am specifying the bending moment and the shear force. Okay. That is, the bending moment and the shear force are given. So this is our Neumann end. Now it could be the bending moment and the shear force could be 0, which corresponds to a free end. So this is a Neumann boundary condition. I could have another situation where I am fixing the middle line of the bar of the beam at this point. Okay. So what I am saying here is v at this point is equal to 0. Okay. Now if v is 0, then I am actually allowed to give a moment if I want, a rotation. So I can apply a moment m0 or leave it free. Okay. So this is called a pinned end. You see that, remember what we had said is the displacement and the shear force occur together in pairs, and the bending moment and the slope occur in pairs. So if the displacement is specified, certainly I can't specify the shear force, but here I have done nothing about the slope, so I can apply a bending moment there. I have to apply a bending moment there because slope could be anything. Okay. In general, see, in most of the examples that you see, this bending moment is set to be 0. Okay. Similarly, I could have another special boundary condition where I have this bar moving in a guided slot, and this is a rigid support. So the rigid support is moving in a guided slot. So what happens, because of this, I have the dV dx at x naught is equal to 0. It is not allowed to bend. Okay, but I could certainly at the same time specify a shear force V naught. So we have the various types of boundary conditions. One can take many more, but these are quite sufficient, at least for most of the problems that we are looking at. Okay. So these boundary conditions can also be incorporated now, just exactly like the way we did it for the second order or the bar problem. These can be incorporated for the beam problem, where IBC type at the two ends. Now this IBC type can be given various numbers. 1 means clamped, 2 means pinned, 3 means free, 4 means rigid free, that kind of rigid on a roller. So we can give these flags at each end, and according to the flag we specify what is the data which has to be inputted. Okay, and accordingly, because dV dx, for example, here is fixed, so I have to go and constrain the dV dx to be equal to 0 in my final system. So once I have obtained the element calculations, done the assembly, then now I appropriately apply the boundary conditions, that is, add either the boundary forces and moments or constrain the boundary displacements or the slopes to be the given values. Okay. Again, the same procedure that we had followed. So once we have this, then now we are in a position to solve the problem. So we can solve this problem in terms of how many unknowns. If it has any LEM number of elements, then I have any LEM plus 1 nodes. Twice into any LEM plus 1 is the NN DOFs, the total number of degrees of freedom that we have, and that's all. We solve for that many degrees of freedom, get the solution, okay, and we are done. Now another thing that you should be able to do now, we had done the principle of virtual work. We could also derive everything that we have done from the total potential energy, where the strain energy is given by, as you know from your basic mechanics, EI of x minus integral x is equal to 0 to L q v dx minus m v prime at 0 and L minus v into v at 0 and L. So if I define the total potential energy like this, which is what we have, the strain energy due to the bending, work done by the distributed force, work done by the end moment, the work done by the end shear forces, then by taking the first variation of this, we should get exactly the weak formulation that we have obtained. Okay. Now the question is that, this was just a remark, we could derive it any way we wish, okay, that how do we post process the solution, what is the information that we need. So out of this, if I have this beam, I will be interested in the bending moment distribution, I will be interested in the axial stress sigma xx distribution, I will be interested in sigma xx max at a point, okay. I may be interested in the shear force at the point. These are the quantities that I may be interested in to get from our finite element solution. So, how will I get to m of x? So, in an element ik, I could do it globally or I can do it in the element. This m of x is equal to m in the element ik is equal to ei x into d2v dx squared in the element ik. But this, if I can write it, it's I is equal to 1 to 4 alpha ik nik double prime whole thing into ei of x. So, I take, now I know what this alpha ik corresponds to from the global to local enumeration. So, I find this value, okay, this is alpha 2 k minus 1 plus I, okay, find the value of this degree of freedom, multiply it with the second derivative of the shape function that we have, obtain the value of the material properties, the flexural rigidity at the given point x, okay. This way, put it in, I can find the value of the bending moment at any point in the element. So, by interpolation I can find. Similarly, for the shear force in this case in the element, if you see, it will be minus okay. So, let us assume for the time being that ei is constant, then this essentially means that it is nothing but the third derivative of v, which in the element is a constant because we have taken a cubic. Okay. So, vi in the element for a constant flexural rigidity, okay, uniform flexural rigidity is a constant. Okay. So, post processing is not a problem. If ei is not a constant, then I go and put it again in the formula that we have written. So, this way we can find the bending moment and shear force at every point. Now, given the bending moment at a point x, finding sigma xx is not a problem. It is equal to mx, so at a point y by I. So, this will be equal to sigma I is equal to 1 to 4 E alpha I k into nik double prime into y. So, at where is it maximum? At the top or the bottom? So, I go to plus minus h by 2 or whatever is my maximum value of the y, because it may not be that the neutral axis is at the midpoint. Okay. Neutral axis could also be shifted depending on what is the cross sectional parameter. So, I will find that the top, the value of this at the top and the bottom, and see which one is the higher, and that is how I will find sigma y max if I need to. Okay, sigma x max. Now, how good are things? So, if I go and look at the value of, so given a mesh, the values of alpha for a node 2i minus 1 and alpha 2i for a node I, okay. These values correspond to v at this point, this corresponds to theta at this point. The values are exact if ei is equal to constant. So, for constant flexural rigidity, the nodal values of the displacements, that is the alphas that we have obtained, they correspond to the transverse displacement and the slope at this point, and they turn out to be exact provided ei is constant. If it is not constant, if ei is not constant but it is smooth, then the nodal values are very good but not exact. Okay. Similarly, I can talk of now how the bending moment behaves. So, if I have this cubic approximation, I will find in an element the bending moment. If I look at the error in the second derivative, it will do something like this. So what I will get that d2w Fe dx squared is very good at actually the points corresponding to the 2-point integration rule, that is at psi, if I go to the master element, plus minus 1 by root 3. So these are the points where the second derivative of the w are going to be very good. Okay. Similarly, because the second derivative of w here is a linear. Similarly, so if I say that, then m of x is equal to ei x d2 wfe dx squared is very good at 2 points in the element, and these 2 points correspond to, in the master element, psi equal to plus minus 1 by root 3. Similarly, if I talk of v of x, okay, this will be very good at the center of the element. Okay. So these are certain things, or we can say it corresponds to the point psi corresponding to the 1-point integration rule. Okay. So essentially, if I really want to pick up values of the good values of the mx and v of x, I can pick them up at these points. Okay. Now there is another question, that imagine that I would now like to get a good value of m of x or v of x, let us say m of x in at every point in the element. So again, what will I do? I have essentially the neighbors k minus 1, k plus 1. For the neighbors, I know that there are 2 points where for each of the element there are 2 points where the second derivative of w is good. So I will take these points and let us say psi 1 of k minus 1, this is psi 2 of k minus 1, and so on, psi 1 of k, psi 2 of k. I will number them in a sequence. So there are 6 such points. So I will call it 6 points psi I bar. Okay, in this set of 3 elements. Then now if I look at this, del 2w dx squared is a linear. So I will now say that I want to get to an approximation which is quadratic. Okay, this is quadratic. Then I will define how will I find these coefficients, and I hope that what I am getting is better than what my finite element solution gave me. So I am going to define a j which is sum over I is equal to 1 to 6. So this is for the corresponding to the element k, okay, of ei at the point x corresponding to the point psi I bar, okay, into d2w star dx squared at the point x corresponding to psi I bar minus d2w fe dx squared at the point corresponding to psi I bar whole squared. So I define this discrete sum over these 6 points, where the 6 points are the 2-point rule points in the elements k minus 1, k and k plus 1. So this I will define for the element k. Now I want to minimize this. So I want the coefficients a0 k, a1 k, a2 k such that this is minimized. I get the set of equations knowing what is my WFE, this is known. I can find d2w star dx squared, and from this fit, okay, I can find these coefficients a0k, a1k, a2k, just like we had done in the earlier case. Once I have obtained these coefficients, then I go and say that my m star is equal to EIX. So, m star in the element k into a0k plus a1kx plus a2k x squared. So, you see, if I go back again, this exercise, this fitting has to be done for each element, where for the element I take the two neighbors, and from there I am actually fitting this quadratic polynomial using the values at these 6 points. Okay. So, once I have done this, then for each element I can construct the solution, and I can construct the m as I have constructed the m. So, I can construct the sigma xx star at the element k is equal to E into a0k plus a1k x plus a2k x squared into y. Okay. So, this is how we can construct the recovered value of the stress. This is essentially an extrapolation of what we had done for the second order differential equation. So, this is also a patch recovery method, but used for the beam problem, and you could see that this will give quite decent values of the recovered bending moment and the actual stresses that we obtain. Okay. So, now you see that we have been able to reach a proper procedure of solving for the actual bar problem and actual beam problem and a beam problem. Now, in general, I could also look at some extensions of this. Maybe that my beam is sitting on an elastic support that is on a distributed spring. So, with this I will only change the stiffness matrix part, that is to the stiffness side I am going to add k of x VFE into W dx. Okay. I could have my member supported by one spring, then at this point I have to ensure that I have a node, and at this point I simply go and take care of this by adding k naught to the stiffness, to the diagonal entry corresponding to the displacement at this node. So, these are certain things that now can be easily handled, and I could also handle the problem where I have a distributed load which is transverse and an axial force and an end load. That is, we can look at the combined beam bar problem. Okay. That is, both in plane loads and transverse loads are there. In this case we will also have the axial displacement. The axial displacement will give me a second order differential equation, the transverse will give me a beam which is the fourth order differential equation. So, we can combine the two and solve the problem. Okay. In this case what will happen, that at every node we will have the u 0, the v and the dv dx as our unknowns. So, there will be 3 unknowns, which is not a big problem. Once we have understood how to do these things, then we can handle this. So, essentially in one dimensional problem this is all we are going to look at. In the next class we are going to start on the 2-dimensional boundary value problem, and we are going to elaborate on how to go about adapting whatever we have done without major changes to the 2-dimensional problem.